Hello friends, here in this video we will see a problem which is based on Brayton cycle. Here is the question, and whatever is given in this question I'll write that in the form of data first before saying what is the unknown which we have to calculate.
So
in the data part, first it is given that a gas turbine is supplied with gas at 5 bar and 1000 Kelvin and expands adiabatically to 1 bar. So to understand this condition, first in the data itself I will draw the gas turbine plant. So before reading the question further, here I will draw the gas turbine plant. Now here the diagram which I have drawn, it is of simple open cycle gas turbine plant. So this is the diagram of a simple open cycle gas turbine plant. Now here if we see, there are three basic components: compressor, combustion chamber and turbine. Now when we see that the process gets started, at first, that is state number 1, the atmospheric air is inlet to the compressor. Next, after passing through from state 1 to state 2, that is inside the compressor, the air gets compressed and we have an air at a high pressure, high temperature. So this is the compressed air. Next, inside the combustion chamber, the fuel is sprayed. So I'll write this as mf, that is the mass of fuel, and in terms of dot if it is in terms of second or minutes, that is time basis. Next, here we have state 3 where we are having gas, and gas is a mixture of air and fuel. That is, after the combustion chamber we have the mixture of air and fuel. That same mixture goes into the turbine, and at the exit of the turbine we have state 4 wherein again we have gas, that is air plus fuel, and that gas which we are having here, it is the exhaust gas. Now, so here is a simple open cycle gas turbine plant. Now I'll read the question again and explain it on this diagram. Here it is given, a gas turbine is supplied with gas at 5 bar. This pressure is above atmospheric and 1000 Kelvin, and then expands adiabatically. It means the initial state which they have given in the problem is before the entry to the turbine, because in the turbine the gases are going to expand adiabatically. So the state which they have mentioned is state 3, that is before the entry to the turbine. So the first thing is the pressure which is given is P3, which is equal to 5 bar, or it is 5 into 10 raised to 5 Newton per meter square. So they have given 5 bar pressure, that is the pressure at inlet to the turbine, and the temperature is 1000 Kelvin. So temperature will be T3. Kelvin, then and expands adiabatically to 1 bar. So in this turbine, the gas which is entering at point 3, it will expand from 3 to 4 and the pressure is 1 bar. So after expansion, that is at point number 4, the pressure P4 is 1 bar, that is 10 raised to 5 Newton per meter square. Next, the specific heat at constant pressure and constant volume are this much, so I'll write the value. Specific heat at constant pressure, C suffix P, 1.0425 kilojoule per kg Kelvin, and the specific heat at constant volume, C suffix V, 0.7662 kilojoule per kg Kelvin. Next, the question is, first draw the TS diagram to represent the processes of simple gas turbine system. So for this simple gas turbine system, we have to draw TS diagram, that is temperature entropy diagram. Next, calculate power developed in kilowatts per kg of gas per second. So this per kg of gas per second is nothing but the mass flow rate of gas, and that is equal to 1 kg per second, the mass flow rate of gas. And for that we have to find out power developed in kilowatts. And apart from that, we even have to calculate and exhaust gas temperature. Exhaust gas is at point T4, so the temperature T4 is what we have to calculate. Now this is the data available to us. With the data available, and we have already drawn the simple open cycle gas turbine, the first question is to draw the TS diagram. So here I'll start with that in the solution part. Now in the solution to this question, the first thing is to draw the TS diagram. So I'll write down TS diagram for simple open cycle gas turbine plant. So now here I will draw the TS diagram for simple open cycle gas turbine, and for that I will require the processes. So now in the TS diagram, here I'll write down the processes. The processes that take place in simple open cycle gas turbine plant and it works on Brayton cycle. R. So here I'll mention the processes, and this simple open cycle gas turbine, it works on a cycle. So I'll write down the type of the cycle is Brayton cycle, which is the governing cycle for gas turbine plants. Now the processes are one to two, reversible, adiabatic, also called as isentropic, compression. Next, process 2 to 3 is constant pressure, heat addition. Next, process 3 to 4 is reversible, adiabatic or isentropic, expansion. Process 4 to 1 is constant pressure, heat rejection. So these four are the processes in case of simple open cycle gas turbine. So I'll start one by one. Process 1 to 2 is reversible, adiabatic or isentropic compression. So that isentropic compression takes place inside the compressor, that is from 1 to 2, and it will be shown on TS diagram with the help of a vertical line from point 1 to 2. Here the entropy remains constant, that is S1 is equal to S2, but the temperature will go on increasing from T1 to T2. So this is the reversible, adiabatic or isentropic compression process, wherein entropy remains constant but temperature increases. Next, from process 2 to 3, it is constant pressure heat addition. So here I'll draw a constant pressure line. Since heat is added at constant pressure, the process will follow this line from 2 to 3, wherein the pressure of point 2 and point 3 both are same because they lie on the same constant pressure line. Now the temperature, as we see, is going on increasing from point 2 to 3. So as we see, during the heat addition process, the temperature goes on increasing and even the entropy will increase from S2 to S3. Next, process 3 to 4 is reversible, adiabatic or isentropic expansion, that will be shown with the help of a vertical line. So from 3 to 4, the process is reversible, adiabatic or isentropic, that is entropy remains constant, S3 is equal to S4. and temperature drops from T3 to T4. So this is the reversible adiabatic expansion process. At last we have constant pressure heat rejection. So heat is rejected keeping the pressure constant. Again I will draw a constant pressure line passing through point 1 and 4. And if we see in the diagram, this 4 to 1 is not a complete process, but at point number 4 the exhaust gases are sent out or thrown out into the atmosphere, so they are not coming back into the compressor. So 4 to 1 is not a complete process. So here I denote process 4 to 1 with the help of a dotted line which indicates the heat rejection process. And if we see here, during process 1 to 2 it is compression process inside the compressor, so work done in compression. Next, during process 2 to 3 the heat is added in the combustion chamber. During 3 to 4 there is expansion in the turbine, W suffix T, and during process 4 to 1 there is heat rejected into the atmosphere. So this is the complete TS diagram which have been asked in the question. So here this will be the first answer for us. Next, in this question they are saying to calculate the power developed in kilowatts. See, power is developed inside the turbine. So I will write down that it is the calculation of power developed. Since power developed in the turbine is given by W suffix T is equal to mCp, and the temperature difference for the turbine is T3 minus T4. So mCp T3 minus T4 is the formula of power developed for the turbine. Here I will keep this as equation number 1. Now in the data, if we see, T3 value, that is the temperature of gases entering the turbine, is 1000 Kelvin given, but we don't have the value of T4. Similarly, M and Cp, they are given in the problem, so we'll go for the calculation of T4, and for that I'll use the pressure ratios. That is, therefore for process 3 to 4, which is reversible adiabatic expansion process. So now, reversible adiabatic expansion process, for that I can write down the relation T3 upon T4 is equal to P3 upon P4 raised to gamma minus 1 upon gamma that is, I have utilized this process 3 to 4, which is reversible adiabatic expansion. So T3 upon T4 is equal to P3 by P4 raised to gamma minus 1 upon gamma. Now therefore T3 value is given in this problem as 1000 Kelvin. T4 value we don't have. P3 by P4, P3 is 5 into 10 raised to 5 Newton per meter square and P4 is 10 raised to 5. So if we write the value in terms of bar or Newton per meter square, it won't make any difference, because here also 10 raised to 5, 10 raised to 5 will get cancelled out. So P3 by P4 can simply be written as 5 by 1. That is, even if I am writing it in terms of bar, the value will remain same as that in terms of Newton per meter square. Now gamma is what we have to calculate, because in this problem Cp and Cv values are given which are different. So here I'll say that in the data itself I can write down, since gamma is equal to Cp upon Cv, so Cp value is 1.0425 kilojoule per kg Kelvin, Cv is 0.7662 kilojoule per kg Kelvin. So from this I'll get the answer of gamma as, it comes out to be 1.36. So now I'll use this value of gamma, 1.36 minus 1 upon 1.36. So from this, therefore, keeping T4 on one side, on the other side we have 1000 divided by this entire right hand side. If I calculate, the answer is 1.53. so 1000 divided by 1.53, therefore T4 comes out to be 653.59 Kelvin. Now after getting the value of T4, I can put all values in equation number 1. So therefore put all values in equation number 1. So we have the turbine work is equal to, it was mCp T3 minus T4. Now m value is given, which is the mass of gas, as 1 kg per second. So here in equation 1, where I have written m, that is m suffix g, that is mass of gas, and specific it is also for gas. So the mass of gas is 1 into Cp value for gas, it is 1.0425. Then the temperature difference is T3 minus T4. So T3 is 1000 minus T4 is 653.59. So on calculating the entire terms here, I'll get the turbine work as 361.13 kilowatts. Here how I am getting the answer in terms of kilowatt, that I'll explain. This is the second answer for us. Here the unit of mass, which is kg per second, which is the mass flow rate. Specific heat is kilojoule per kg Kelvin, and temperature difference is in terms of Kelvin. So kg will get cancelled out, Kelvin will get cancelled out. Kilojoule per second is nothing but kilowatts. So here I am getting the answer in terms of kilowatts, the amount of power developed inside the turbine. Next, temperature T4, which is the exhaust gas temperature, that already we have found out. T4 is the exhaust gas temperature, so which is 653.59 Kelvin. This is the third answer. So for the calculation of turbine work, temperature T4 was required. We had previously calculated, and this is the third answer, that is the exhaust gas temperature. Now if we see, all three unknowns have been found out, and with this we complete the problem.